Hello, this is Chris, and welcome to the second video in the Vector Extra Credit Opportunity. In this video, I'll be discussing I'm going to call it the theory of coordinate spaces and some general applications to vectors, how to use coordinate spaces to calculate and find vectors, and how to calculate with vectors as well. So right here, we have a grid. This is a normal XY grid. It's what you've been doing in math for ever. It's an x direction is the horizontal and the y direction is the vertical. And every step in the x direction is equal to every step in the y direction. And I really want to spend some time to explain what that means by step. Imagine that you have this grid on your front porch. Okay, so let's say you have a front porch, and this front porch is this grid. Now, if you were to walk one step forward, so your human step, one left foot or right foot, whatever, that distance that you travel, let's say that every step you take is 2.5 feet of a distance. So you go towards the end of the porch, one step, and then you turn left or turn right and you step another step. So 2.5 feet in that direction. You have traveled 5 feet total. If we were to consider one of your steps, one of your strides, as the unit change in that porch, then the unit change in the x direction and the unit change when you turn around, the y direction, is the same because of the way that the grid is laid out. In other words, let's say each of these big tick marks is 1 foot. So you stepped 1.5 feet. Whoops. So 2.5 feet. I can't count. So you stepped and you landed right about here, right? You started at the origin. You started somewhere, and we're going to call it the origin. And you moved in a direction 2.5 feet. You're right about here. And then you turned left and you moved up another 2.5 feet. So now you're right here. And you've traveled 5 feet of distance. But 5 feet of distance is 2 units. 1 unit of x and 1 unit of y. So why does this actually matter? Because when we have a non-planar coordinate system, such as a sphere, things get really funky really quickly. And actually, let me drag in a new sphere because maybe this sphere is easier to see. I don't know. God, sometimes this program takes. No, I do want it solid. Whatever. Sometimes this program takes an absolute arbitrary amount of time to make it brown. Hopefully the color contrast. I don't know. It's lagging a lot, so bear with me. Anyways, so we have 2 coordinate systems. We have the planar coordinate system, which is right here in the background, and that's the xy. This is the xy plane, and the height is going to be the z-axis. We have an x, y, z coordinate space. This is called the Cartesian coordinate space. I'm going to use the word Cartesian a lot. And can I please just zoom in? Is this a possibility? Is zooming in a possibility? Oh my God, why is it doing this to me? And the second space is the wow, this is just pathetic. Let me restart it. So the second space is the spherical coordinates. So spherical coordinates are not just in this nice square grid. It's wrapped around a sphere. And really kind of what I want to go into is this idea of how coordinate systems change for incremental differences. An incremental difference is like you take a step forward, you take a step to the left. It's each one of those steps is an increment. I'll just use this as an example because it'll have to do. Um, Notice that if I'm looking at this, I don't know how well it's going to show up on the video, but if I'm looking at this center, this top of the sphere, outwards, we have lines just going outwards, and we have lines that are wrapping around. So we have circles around the center here and lines going outwards. This is literally just a polar coordinate map wrapped around a polar coordinate map. So what's happening with this coordinate system? Well, each incremental step is a little bit different. In other words, how can I move on this surface of the sphere? Well, I can move up in latitude, down in latitude. I can move up in longitude and down in longitude, and I can also move inwards and outwards. So I can get closer to the center of the sphere and farther away. Now, that's actually really cool because what we're going to do is we're going to figure out why these things are different. Notice that this equator right here, this little change right here, this distance between this point, this line and this line is the same distance between this line and this line. And there's no way of really measuring in this program, so I'm not really going to prove it, but trust me on this. The distance between this line and this line is the same no matter where you are, above or below the equator. And why is this? What does that mean? Well, these are latitude lines, and we're going from one latitude on the line to another. So we're changing latitude. So latitude. So let me back up. So if you change x, what you're doing is you're kind of staying in the same x direction, and you're just going forward or backwards. And but with latitude and longitude, when you say you change latitude, you're actually going perpendicular to the latitude direction. The latitude direction wraps all the way around the Earth like the equator because the equator is the largest latitudinal line. And that's what happens. So if I'm moving along in a latitudinal direction, that's along the equator. But if I'm changing latitude, that's not me wrapping around the equator, that's me going to a different latitudinal line. And it's the same thing with longitude. Longitude is north and south. So longitude are these vertical lines. And notice that the distance between each of these vertical lines is going to be smaller and smaller the closer you get to the poles, and farther apart the farther away you are from the poles. And the equator is the farthest distance. In fact, at the equator, the change in latitude equals the change in longitude. But anywhere else, this fails to hold. So in order to express a coordinate in Cartesian plane, x, y, and z, we would just represent it as x, comma, y, comma, z. And that's exactly how you would represent it in terms of spherical. Latitude, comma, longitude, comma, elevation. But those differences matter. So let's say I'm at 100 degrees latitude, 100 degrees longitude, and 100 feet in the air. So if I add 100 to each of those, so 100 degrees latitude becomes 200 degrees latitude, and then 100 degrees longitude becomes 200 degrees longitude, and 100 feet in elevation becomes 200 feet in elevation. I did not move twice the distance. And here's why. So 100 degrees latitude is, well, actually, now I think about it, 100 degrees latitude is kind of impossible. So let's pick something smaller. 45 degrees latitude. So here's how you measure latitude. How about I go over that first? So the equator is 0 degrees latitude. The poles, the North Pole is 90 degrees latitude, and the South Pole is negative 90 degrees latitude. The longitude, 0 degrees longitude, is the prime meridian, which is what this line is, this plane, this vertical plane that's cutting the sphere in half, that denotes the prime meridian. And this horizontal plane denotes the equator. So this is the prime meridian, and that's longitude equals 0. So 0 degrees longitude is at the prime meridian. And the prime meridian wraps 180 degrees. So every time latitude hits 90 degrees, it resets and starts to go back downwards. In other words, I'm at 89 degrees latitude right here, 90 degrees latitude. And then when I keep going in this direction, now I'm back at 89 degrees on the other side of the world. For longitude, I'm at, I'm at 179 degrees longitude, 180 degrees longitude, and then I'm back over to 179 degrees longitude right here on the other side of the world. And so these things, and also works the same way with negatives. I'm at negative 89 degrees latitude, and then I go to negative 90, and I'm at the South Pole, and then I go back down to negative 89 by crossing the South Pole. And that's kind of how we measure latitude and longitude. Now, this is important because if I say we started at 30 degrees latitude, so roughly about here, and we started at uh, 60 degrees longitude, then that's roughly here. So that's roughly right here on this place, right? Now, if I were to add 30 degrees latitude and 30 degrees to my longitude, then 30 degrees latitude is up here and 30 degrees longitude is way over there. But notice that each degree is really represented by this vertical line. Each one of these, a 1 degree, this is 1 degree, and if I move up a little bit, this is 1 degree. In other words, the same degree difference in longitude is actually corresponding to a different distance traveled. And that's what makes this coordinate system so difficult to work with. Also, elevation is kind of funky because um, in reality, this is supposed to be a sphere. And so, really, the only thing that matters is the radius of the Earth. You have things like elevation. There are mountains, and even the ocean isn't perfectly flat. So you have variations in elevation, which actually correspond to an increased change in latitude and longitude. And that's what's so screwy about this coordinate system. So how do we work with it? What does it mean to be, say, a vector in Cartesian versus a vector in spherical? So a vector in Cartesian is an arrow. It is a straight line. It's y equals mx plus b. That is a vector. Actually, yeah, a true vector is y equals mx plus b. But an arbitrary vector in Cartesian is y equals mx. It's a line from the origin to whatever point that you want. And that's traditionally what a vector is in Cartesian coordinates. What is a vector in spherical? Well, a vector in spherical is a magnitude in a direction, but the direction is a little bit weird. So notice that these circles that wrap all the way around, those, as I said in the previous video, these are actually vectors in spherical coordinates. This is what is considered a linear vector in spherical coordinates because it is constant elevation. A plane traveling at 30,000 feet in the air is going to stay at 30,000 feet in the air. It is able to stay at 30,000 feet in the air, regardless of where it is on the Earth. And this is actually the important part to understand. That means that it's a circle. So vectors in Cartesian are straight lines. Vectors in spherical are actually circles. And other coordinate systems get even funkier. But what is what does it mean to have a distance between 2 points on the sphere? We know the distance between 2 points on Cartesian coordinate. That distance between 2 points on a Cartesian XYZ space is the straight line distance between them. But I don't want that because that would mean that I'm going through the Earth to get to these 2 points. If I had a point here and a point here, then the Cartesian distance between the two is literally the straight line connecting those 2 points. Well, that's actually really stupid because that's going through the entire Earth. I don't want the distance between Las Vegas and Orlando, Florida, as if you carved through the Earth. I want the distance as if you traveled by boat and as the crow flies, I guess. So that is a vector. I'm asking for a directional vector in spherical coordinates. In other words, I want a circle that is defined between 2 points, and that's exactly what I have. A circle that wraps around the entire sphere, the maximum possible, the biggest possible circle that you can wrap around a sphere and still stay on the sphere, that also intersects 2 points, is called the great circle between those 2 points. In other words, every single great circle has the same radius. It's the radius of the sphere. The equator is a great circle. It's the only latitudinal great circle. Every longitudinal line is a great circle. So really what's happening is, and the reason why, let me back up. The reason why is because notice that these circles are getting smaller and smaller the closer you are getting to the poles on either side. And that corresponds to a decrease in the maximum possible circle that you can have along the latitudinal lines. This is precisely why the maximum great circle that can be achieved is really just the equator for latitude. So I really want to figure out a way to go from 2 points along a circle in which that circle's radius is the same radius as my sphere, and it has to pass through those 2 points. Well, this is actually a really difficult problem that took not scientists, it took mathematicians about 1,000 years to figure out. So no, you guys will not be figuring that out. I didn't either. So what we're going to do is we're going to um, use existing formulas to greatly approximate this path. And then we're going to take this path and kind of think of it as a linear distance because these 2 points are really close together. Now, before I go any further, uh, I want you to go and I will give this PDF. Uh, I'll probably give it in the email as well, but I'm going to see if I can have the professor put this in Canvas for you guys. And this is basically a tutorial on how to do this. You still have to do work and you still have to think about whether it's correct, but nevertheless, this shows you how to do it. I want you to watch this video before you go past this concept. This guy explains the process of calculating the great circle distance between 2 points using trigonometry. And he does an excellent job doing that. Now, I'm not using that formula. That's the formula that I actually came up with before I watched this video. But I'm not using it because it's not accurate enough. It's not good for small angles. And we're talking about places on campus relative to the entire Earth. So if you're at the center of the Earth and you want to find the angle between where I'm standing in Sugar Pine and where I'm standing in Manzanita, I can guarantee you that angle is incredibly small. And that produces floating point errors in the calculation. And that's a problem. And you're definitely not going to be able to do it by paper. So you kind of need to use your calculator, and your calculator can't do it accurate enough. So I'm going to use a different approach to. Uh, I'm basically just going to use a completely different approach um, that uses linear algebra and sums. some, not a lot, but some multivariable calculus concepts. And this is a good opportunity to kind of see what's going to happen in future math courses you take if you choose to do so. Um, and a great introduction to some of the concepts of linear algebra, which is all about vectors and matrices. Um, so let's jump into it. So, what are vectors and why are we using them? A vector is simply a mathematical object that contains two categories of information. It contains a magnitude and a direction. People love using vectors because just by looking at the vector itself, I can figure out where it's going and how far. The properties are magnitude and direction, and I can just describe them simultaneously. Now, each building, I am requesting two vectors per building, but there's actually four vectors total. The first vector is the vector I'm going to ask for. It's the direction vector. The third vector is the other vector I'm asking for, and it's the tilt vector. You must find a primal vector in order to figure out the tilt vector. And the other vector is this thing that's sticking out right here. These arrows, these big green arrows are representing vectors, which is a magnitude and a direction. The direction is pointing outward, perpendicular to the surface, and the magnitude is whatever the magnitude is. And I'll get to that in a minute. Basically speaking, what we're really going to do is if we're going to convert XYZ coordinates into latitude and longitude or vice versa, then we're going to need a way to squish down the coordinate space such that it accounts for the fact that a step in latitude is a different quantity than a step in longitude. In other words, it accounts for the fact that this is a circle and a sphere, circles on a sphere, instead of just squares on a larger square grid. And that being said, there's really two ways that we can go about doing this. We can we can calculate the distance after we have fixed the coordinate system, and this straightens out the air quotes bending of a spherical coordinate system. And that bending corresponds to the fact that two parallel lines on a sphere, they start parallel, as it turns out, they intersect. I mean, think about it. All of these longitudinal lines are parallel. They start at the equator and they're parallel. They're all the longitudinal lines are parallel at the equator. And then they somehow intersect, and where they intersect is the poles. And that's hard to understand. That parallel lines intersect on a sphere. It defeats the purpose of being parallel, doesn't it? Well, magic like that is what allows the bending of the coordinate system to take place. It's what allows the fact that a change in longitude is different than a change in latitude. The one-to-one correspondence between one of the directions and the other direction is actually different because of the fact that parallel lines intersect. So we can fix the bending and then plug in a bunch of stuff, which is what this is. Or we can ignore it entirely and use vectors, which is what this is. Now, I don't know about you guys, but this formula looks a lot nicer than this formula. I mean, damn. This thing right here is awful. This is 2 times the radius of the Earth times the arctangent of the square root of cosine squared of your latitude to the second point times the Haver sign of twice the change in your longitude plus the quantity cosine of your latitude times the sine of your of the latitude to the second point minus the latitude of the first point times the cosine of the latitude of the second point times the cosine of the change in longitude, all that quantity squared, and then that whole square root thing divided by more stuff. The sine of your first latitude times the sine of your second latitude plus the cosine of your first latitude times the cosine of your second latitude times the cosine of your change in longitude. And that's ridiculous. Now, the cool and the convenient thing about this formula is that it only takes latitude and longitude. That's all it does. You just plug in all your values. You have to take your latitude, your longitude of your second point and subtract it from your longitude of the first point to get the delta lambda to get the change. And you have to convert this Haversine into something that's something your calculator can use. These are identities, by the way. But oh my God, why? Why would you want to do this? This is ridiculous. And actually, there's a problem with this because even though this has very little issues, this thing is generally less accurate than this thing right here. And you might say, well, why would they have a nasty formula that's 3 times inaccurate as a formula that's much nicer? Well, the reason why is because this formula existed long before this formula did. This is a modern approach, and this is an ancient approach. This is something that you would explain to Galileo, and this is something that you would explain to Einstein. They're just different time periods. And so the density of information is a lot more massive in this equation than it is in this one. So we're actually going to ignore this. This is, if you want to know, I gave a link to the Wikipedia page. This is Vincenti's formula, and it is an alternate to the Haversine formula. That's what this is called, the Haversine. It's an alternative to the Haversine formula, and ironically uses a Haversine in it. And in this method, it is simple. It is simplified by assuming that the ellipsoid is actually a sphere, and that's what makes this less nasty than it really is. This is actually much worse, but I'm assuming that the radius of the Earth in the latitude direction is the same as the radius of the Earth in the longitude direction. In other words, I'm assuming the Earth is a sphere and not an ellipsoid, which is what it really is. Unfortunately, this is drastically overkill with far less accuracy. So I'm going to use the better notation. And this is something that video this video right here. This video he mentions the Haversine formula. And that's basically what this is. This is the Vincenti's formula, but this is also a derivation of the Haversine formula. So please watch this video before continuing on this one. Now let's move on. Let's start looking at the formula that I want you to use. So I'm going to have you guys use the radius of the Earth as 637.008767 kilometers. I have calculated that radius myself. That is the one that I want you to use. It's very accurate. Now, this distance between 2 points is the radius of the Earth times the arctangent of the magnitude of the cross product divided by the dot product. Now, I don't know how far you've gotten with vectors so far in trigonometry, but basically, these three things are basic operations of vectors. If you don't know them now, you should know them for the future. They're very, very important. These things help you a lot in physics, help you a lot in physics. They help you a lot in chemistry, and they even help you a lot in biology. So these things are very useful if you know how to use them properly. So I'm going to explain what these are in a minute. But first, in order to even use this formula, I need vectors, and the n represents normal. That's my notation for normal vectors. The normal vector for your first coordinate and the normal vector for your second coordinate. Now I want you to understand that these normal vectors are three components. They have three components. They have an x direction, a y direction, and a z direction. So these are Cartesian vectors. So I somehow need to convert my latitude and longitude into Cartesian vectors. My latitude and longitude vectors into Cartesian vectors. And before I go in any further, I want to go back to this thing one more time, or maybe I'll do it one more time after that. So these arrows are perpendicular to the surface of this sphere. Let's imagine that those arrows were perpendicular to this plane. They would all be pointing in the same direction, wouldn't they? And that direction, by the way, is the direction of the plane. Now, they all might have different lengths. So these vectors over here, they might have different magnitudes, but they are all pointing in the same direction if they're on a plane. But notice that this plane does a really bad job at approximating the sphere as a whole. So really, we need to be able to consider these normal vectors. So these are called normal vectors because they're normal to the surface that you're operating with. We're operating with a sphere, the surface of a sphere, and normal means perpendicular. So these are just vectors that are perpendicular to the surface of the sphere. Perpendicular to the plane, to the surface of a plane, they're all pointing in the same direction. But every point on the sphere corresponds to a different direction for a normal vector. Opposite sides of the sphere correspond to the opposite direction. So it's actually pretty handy. And this is what we're going to use. This is the magic trick to convert latitude and longitude into something that we can use in X, Y, and Z. And here's the reason why we need to do this. Notice that an XY Cartesian plane, your location is unique. If I tell you go to 3 comma 5, you're going to go to 3 in the x direction and 5 in the y direction. It's a unique position. But latitude and longitude is not unique. 360 degrees latitude is the same as 0 degrees latitude. If I travel all the way around the sphere, I'm going to end up exactly where I started. Oh, sorry. 180 degrees latitude is the same as 100 is the same as 0 degrees latitude, which is also the same as 360 degrees latitude. 360 degrees longitude is also the same. 360 degrees longitude is the same as 0 degrees longitude. And this is kind of my point, is that's a problem. These values repeat. That's a problem. The cosine of 0 degrees is 1. The cosine of 720 degrees is 1. That's a big problem because our values are repeating. That's like saying go to 3 comma 5 and you're at 3 comma 5. But if you go to 6 comma 10, you're also at 3 comma 5. In other words, these values repeat. We can't have that. We need to have a unique representation for every point on the sphere. This is why we're using normal vectors, because no matter where you are on the sphere, your normal vector is unique. Your position is not unique because you can represent it in as many ways as you want, but the normal vector is always unique. So we need to take our latitude and longitude and convert it into a normal vector. So this is kind of like if I had a point in Cartesian coordinates located at, say, 5, comma 7, comma 15, then the vector that describes that is 5, comma 7, comma 15. Now, you represent it in a slightly different format. This is a coordinate point. This is the x, y, and z coordinate. And this is an x, y, and z direction. So as a general rule of thumb, if you have a horizontal vector, a horizontal set of parentheses with commas, then that is a position. And if it's vertical, then that's a direction. So that's uh, A units in the x direction, B units in the B direction, and C units in the C direction, representing it as an arrow pointed at that direction. There's no arrow here. This is just the point itself. And if the origin is, well, the normal origin, 0, 0, 0, then a vector to any point in that coordinate system is just that point written in this vector notation. V for vector and P for point. And notice that this V has an arrow above it. If you see an arrow above something, then that means it's a vector, generally speaking. So a vector pointing in the direction of latitude and longitude does not make any sense unless we can convert into spherical coordinates, because a vector has to point to a location. But I already said that you can go all the way around the sphere in latitude and longitude and get to the same damn location. So the idea is that the location needs to be unique in order to represent it as a vector. So I'm not going to go into the derivation of this because the derivation requires multivariable calculus and linear algebra. And I'm not going to go into that because it's well beyond the scope of the trigonometry class. And there's a lot of things I need to explain beforehand first. It would take about a day or more. So no. Instead, I'm going to spit out this formula for you. This is the normal vector. So this is a vector perpendicular to the surface at this latitude and longitude. And you plug them directly in. And what this means is, remember, this is the A distance in the x direction, the B distance in the y direction, and the C distance in the z direction. So if you take your latitude and your longitude, you convert it into decimals, and you plug those decimal values in for cosine phi and cosine lambda, this will give you the x direction for this vector. This will give you the y direction for the vector, and this will give you the z direction for this vector. Pretty cool, huh? Well, which method should we plug these numbers in? I know it says degrees, so I guess you can cheat a little bit, but think about it. Why does it have to be in degrees? So far we have degrees and we have radians. There's a couple other formats too, but there's radians and there's degrees in the trig class so far, right? I mean, which one should we choose? Sometimes formulas require radians and sometimes formulas require degrees. And unless you've caught on to it early on, there isn't really a rhyme or reason depending for what goes to where. And I'm going to give you guys some intuition for future math classes. That's actually very important. Radians and degrees are angles. They're measurements of angles, but they're actually completely different. They're very different things. A degree is a revolution. It's a portion of a revolution. 1 degree is a 360th of a full revolution. And what this means is that a degree is a direction. I am rotating in a direction. Negative 55-degree rotation. I rotated negative 55 degrees. I pointed in the negative direction 55 degrees of the way. Radians is really just a scaled up or down version of the radius wrapped around the circumference. So radians are actually lengths. They're not directions, they're lengths. So if we think about this n vector, we're plugging in latitude and longitude, right? We're plugging in these coordinates. But latitude and longitude are directions, which is precisely why we can wrap around the Earth in the same direction over and over and over again. Precisely why 0 degrees latitude is the same as 180 degrees latitude, which is the same as 360 degrees latitude, and so on. That's the whole reason why it repeats. Is because it's just a direction. You just keep going in that direction, you'll get repeated values. So these need to be in degrees because I'm plugging in a direction, and so I need to treat it as a direction. It's kind of like I have a car and then I have a truck. I better put car tires on my car and truck tires on my truck. They're both the same kind of thing. They're both vehicles. And tires both do the same thing. They allow the vehicle to move. But truck tires are made for trucks and car tires are made for cars. And so if you want car, then you better have car tires. So I have a direction. And so I better put it in for the direction version of an angle. And the direction version of an angle is degrees. Okay, so enough of that. Um, this I'm not for those of you who are very interested in figuring out where this formula came in. Um, this is you can look it up if you want. This is the normalized Jacobian transformation from R3 Cartesian to R3 spherical. Okay. For everyone else, let's go over what it means, what this equation is actually telling us. So the radius of the Earth, that's a number. Yay, it's a number. I don't have to do anything to it. Arctangent of this mess. So let's evaluate what that mess is, because you know what arctangent is. I'm not going to get into that. But what the heck is the cross product? What is the dot product? And what is the magnitude of a vector or vectors? So again, I'm not gonna derive what it is precisely to be a cross product or a dot product. But I am going to explain the concept behind cross products and dot products because that's far more valuable than understanding. Um, this is like week 10 in linear algebra, or week 3 in calculus 3. So this is advanced stuff as far as knowing how it works. And so I'm not going to derive it, but I am going to explain what it means. And I'm going to zoom in a little bit because um, the dot product has some notation that I want. Both of these have some notation that I want to emphasize. So the cross product, we say that the n1 cross n2. Now, this is a determinant of a matrix. I'm not even going to get into that. But what we do is we pick the I slot here. This is an I, this is a J, and this is a K. The I component, the J component, and the K component. Okay. So this is the I component. We're going to take our hand and we're going to cover up the I component, the row of the I component and the column of the I component. And we're only going to look at what's left. And what's left is N1J, N1K, N2J, and N2K. That's the only thing that's left. And what we're going to do is we're going to cross multiply. That's kind of part of why it's called the cross product, is because we're multiplying in a cross. So it's N1J times N2K minus N1K times N2J. And we're going to call that W sub I. So this is that first portion. And because we covered up the I, this represents the ith component. And that's what I've written down here. N1J, N2K minus N1K, N2J. And then, for some reason that I don't have time to prove, minus the the Jth component. So that means you cover up the J, and you cover up the J's row and column, and you calculate what's left. So N1J, N2K minus N1K, N2J. And that's what we have down here. And notice that, well, I'll get to that in a minute. Never mind. Then the kth component of W, it's added. Cover that up, same process. Row and column, gone. N1J, N2J minus N1J, N2J. Sorry, N1I, N2J minus N1J, N2I. I said that wrong. Now, it's really this whole thing without the W's and D's instead. But the reason why I didn't do that is because I ran out of room and I wanted to make it big because we have double subscripting and one of the subscripts has a vector hat on it. These vector hats, by the way, are a little bit different than the normal vector hats. Notice that these are arrows and these are carrots. Now, arrows mean just whatever vector you want. It's just any vector. But carrots represent a specific kind of vector. And they represent, if you want to look it up, they represent the basis vectors, the standard basis vectors for the coordinate space that you're working in. We're working in X, Y, and Z. So the I is X, the J is Y, and the K is Z. So I represents 1 unit in the X direction, 0 units in the Y, and 0 units in the Z. This represents 0 units in the X, 1 unit in the Y, 0 units in the K, in the Z. And this one is 0 units in the X and Y, and 1 unit in the Z. Okay, so what does it mean now since you know how to evaluate this thing and turn it into these, which I've conveniently laid out? What does it mean to be a cross product? What does this mean? Well, the idea is that cross products are very useful for finding information that is otherwise very difficult to obtain. So the cross product of two vectors actually gives you a vector. Notice that we start with n2, n1 and n2, and we end up with w, where these are the components of w. So we end up with n1 vector, n2 vector, and we end up with w vector. And how does this relate? How are we getting a vector in return? And what does that vector mean? What does it represent? Well, n1 and n2. Let's pretend that n1 and n2 are on the xy plane. W is in the z direction. The cross product is what determines, is actually what produces a vector that is perpendicular to the two vectors that you crossed. And you might say, well, okay, how does this work? How is this a possibility? Why does this matter? Because I want two normal vectors. I want a normal vector for your base point and a normal vector for your origin, right? And the only way that I can calculate a normal vector is by using the cross product. The cross product literally gives me a vector that's perpendicular to both of these vectors. W is perpendicular to n1 and n2 simultaneously. The z-axis is perpendicular to the x-axis, and the y-axis. And actually, what's really cool, you can prove that if you take the positive x-axis and you cross it with the positive y-axis, you get the positive z-axis as an answer. So if you take positive I and you cross it with positive j, you will get positive k as an answer, which is incredible that all this stuff ties together. So next thing is, this is a dot product. What is a dot product? And we say that n1 is dotted with n2. What does it mean to be the dot product of two vectors? Well, unlike the cross product, which makes everything perpendicular, the dot product tells you how much these two vectors agree. And what I mean by agree is how closely, how similar their directions are. So an example is, if you were to actually take the dot product between the x-axis, the positive x-axis, and the positive y-axis, the dot product is 0. And what that means is 0% of those vectors, 0% of any of those vectors, of any portion of those vectors, agrees with the other. Which makes sense because the x-axis is perpendicular to the y-axis. None of it agrees. There's an x direction and a y direction. There are 0 y directions in every x direction, or in any x direction, and vice versa. And so the dot product between two axes is 0. But what if I had two of the same thing? What if I had the x-axis dotted with the x-axis? I would get 1 as an answer. Why? Well, because They agree 100%. So you get a number out of the dot product. The cross product gives you this W vector, and the dot product gives you a number. Notice that these are just, N1J is the N1I is the ith component, the first component of the first vector, the second component of the first vector, the third component of the first vector, the first component of the second vector, the second component of the second vector, the third component of the second vector, right? So this is literally just one component times another, plus one component times another, plus one component times another. And it's not being multiplied by a vector, which means that these things stay numbers. So the cross product is it gives you a vector, but the dot product gives you a number, and that number is the ratio that describes the agreement in the direction between those two vectors. And the last thing that's important for now is the magnitude of a vector. The magnitude of a vector is how far does this vector travel? The magnitude of velocity is the speed, right? So this is actually very important. All you need to know, and I'm not going to prove it. You can prove it if you want. It's a nice trigonometry exercise. It's actually quite difficult, but it is pretty nice. You can prove it, but the magnitude is really just Pythagorean's theorem. So if you had an R2 magnitude, then the length of that vector is the hypotenuse of a right triangle. And the hypotenuse of a right triangle is, well, it satisfies the Pythagorean theorem. There you go. Now, this is actually not just a triangle on a flat plane. This is a triangle in 3D space. And as it turns out, you just add another component and square it. And that is infinitely scalable. So the, the distance between two vectors in the 15th dimension is really just 15 of these squared and add together. So the cool thing about the magnitude is that it takes the ith, jth, and kth components of the vector that you want to magnetize. So notice that this is not n1j or n2j. This is just nj. Right? This is the entire I component of that vector. It's not this is not an operation that relates one vector to another. This relates the first vector to the second one. This relates the first one to the second one. This does not relate a vector to anything else. It's just this is the magnitude. This is what you do. So I didn't really want to keep writing out, all these subscripts. And so what I did was I decided let's make our lives easier. Let's just call the latitude of your origin point capital alpha, the latitude of your base point lowercase alpha, the longitude of your origin point capital beta, and the longitude of your base point lowercase beta. So let's just pretend that these things let's just uh, substitute. There you go. Let's substitute these variables in. So where am I getting all these? Well, this is the WI component. This is the W's J component, and the W's K component, right? So let's look at the W's I component. What does it mean to have the W's I component? Well, let's go up to the definition of WI. WI is this: N1J, N2K minus N1K, N2J. So what this means is the W component is the second component of the first vector times the third component of the second vector minus the third component of the first vector times the second component of the second vector. You might say, well, where the heck are all these components? Up here. This is the first component. This is the second component. And this is the third component. The first vector, by the way, is your origin point. The second vector is your your origin point. The second vector is your base point. So, in other words, n sub 1 is this where you plugged in capital alpha and capital beta for latitude and longitude, respectively. And 2 is this where you plugged in lowercase alpha and lowercase beta for latitude and longitude, respectively. This is very important. This takes the most amount of time. Plugging in all your values and making sure you're doing it right, making sure your answer is somewhat legitimate. Okay? So, I took these data points right here, plugged them into this to get N1 and N2. And then I plugged in those points here to get W in terms of alphas and betas. And that's precisely what I have here. This you would plug into your calculator to get an answer for W, the first component of W, and the second component of W, and the third component of W. And the cross product is this. So I very much conveniently wrote this out for you so you don't make any mistakes, because this is stuff that's actually really difficult to keep track of if you're not familiar with vectors yet. Okay. Now, since we have everything written in terms of W's and the cross product, now we can rewrite that equation as stuff that we have direct values for. This is very important to understand. What is alpha and what is beta? Alpha is the latitude of your origin and base point. And your beta is your longitude, right? Those are directions. And once again, I'm plugging in a direction into a trig function, so I better evaluate all of these in degrees. Okay? But notice right here, we're multiplying whatever the heck this is by a distance. So this is a distance. Distance equals this. So in order to get distance equals this, I need this r distance to be multiplied by a distance. In order for arctangent to become a distance, you need to evaluate this in radians. This is where it gets a little bit tricky. This is why you want to plug things in first. Why you want to plug things in separately. All 4 of these need to be evaluated in degrees. Then you plug it into this, and this you evaluate in radians. And then multiply it by the radius of the Earth, and that's your answer for the magnitude of your vector in kilometers. Okay. It is impractical. It is imperative that all of your trig functions are calculated with degrees until the inverse tangent function is needed to be calculated. Okay. If you use this formula where n1 is your origin point and n2 is the base point, then this result, this distance, is the magnitude of the direction vector. Okay. If n1 is the origin point and n2 is the tilt point, then this distance right here is the magnitude of the primal direction vector. And like I said in the previous video, do not calculate the magnitude of the tilt vector. I will give that to you. Instead, give me the angle of the tilt vector, the orientation of it. And you can get the orientation of the tilt vector by looking at the diagram that I had in the previous video, where it's basic vector subtraction. Vector, primal direction vector minus direction vector is equal to tilt vector. Cool. Now, this is actually kind of a problem, though, because we only have the magnitude of these vectors. We don't have the direction. So right now, these things are nothing but circles like this. Each one of these circles represents a magnitude. It's a magnitude in any direction. The problem is I don't want it in any direction. I want it in a single direction. And these, by the way, this is the CMBB point in terms of all the other points. I just did that. Uh, don't worry about this. This is something that I did. So these are actually other origin points that I put in here, and I've calculated the location of all these points relative to the CMBB point being the origin. And this is what I'm going to be doing with the campus. Instead of each one of these, it's going to be each one of your guys' vectors in this wonderful plan. Now, that being said, this right here is very important. Bearing and heading are different. Bearing is the destination location. So bearing is the latitude and longitude coordinate, and heading is the angle that you need to travel relative to the north that you would need to that would give you that destination. So example is, imagine that I'm in San Francisco and I want to go to Los Angeles. So if I'm in San Francisco, actually I have a course map. I have the course map open. So why not do that? So I'm in San Francisco right here, and I want to go to Los Angeles. So San Francisco's latitude longitude is 37 and negative 122, and Los Angeles is 34 and negative 118. 34 and negative 118 is the bearing. The heading is the angle that I need to travel relative to the north direction to go to Los Angeles. And it looks to me about 175 degrees. And this angle, by the way, is clockwise off of the north direction. It's a northeast angle. I think I have that up here. Yes. See, can I make that full screen? Nope. Cool. Notice that it starts at 0 degrees on the north and it goes clockwise. So the bearing is the destination itself, and heading is the angle that you have to travel to get to that direction. In order to calculate heading, you're literally calculating the angle between both of those vectors, which you know how to do in trig, right? So this is basically a fancy way of saying that. Remember what beta and capital beta are. This is the point, this is your base point longitude and your origin point longitude. So this is sine of the change in your longitude times the cosine of your final longitude. This is the cosine of your initial latitude times the sine of your final latitude, minus the sine of your initial latitude times the cosine of your final latitude times the cosine of your change in longitude. All these formulas look pretty much the same because they kind of are. Notice that this says initial heading. The idea is that this is an angle, right? This is an angle theta. The thing is that theta changes because of the way that we calculate theta. Theta is an angle on a flat space, but we're not in a flat space. We're in spherical. And so theta actually changes while you're traveling the Earth. So the initial heading is what I would like you to calculate in order to be familiar with this. But what I want you to provide as part of your answer, so when you give me a vector, you're going to give me the magnitude of that vector, which is this formula. And then you're going to give me the direction of that vector in your final heading. And this website right here is this one right here. Make point 1 your origin point, and make point 2 your your base point, and it will give you the initial bearing and the final bearing. This is a great way to check your work for initial bearing, and this right here is the angle that I want for the orientation of the vectors that you're going to give to me. Now, last little bit here, very last little bit is is to combine the magnitude and direction data into the vector that we want. So both the direction vector and the primal direction vector can be figured out using this. This right here is the same d as this. So it's the magnitude of one of these vectors. So if you chose the magnitude of your direction vector, then make sure it's the cosine of your final bearing. Sorry, the magnitude of the direction vector times the cosine of your final heading for the x component. For the y component, you're going to take your direction vector's magnitude and times it by the same theta final heading. And E, do not worry about E. Write E as your final answer. This is the elevation. It's a fancy little E that I'm doing for elevation. And this is data that I'm going to get from Professor Jeff Tolhurst's ArcGIS class. So with their drone mapping, they're going to tell me what the elevation is precisely, and I'm just going to stick that elevation in here. And to calculate the tilt vector, you need both of these vectors in this completed form. And what you're going to do is you're going to subtract d from d prime. And how you subtract vectors is you take the x component of the first vector and subtract it from the second component of the first vector of the second component. So x minus the I component minus the I component, the j component minus the j component, the k component minus the k component. And notice that when you do that, you should get, as your tilt vector, you should not have an E as your final elevation. Why? Because it's a building. Hopefully, the building is level. There are some exceptions, like Redbud. Redbud is the Redbud and no, pretty much Redbud. Just Redbud is the Fire Academy building, and that has stairs. And so, do I have it on the map? I think I have it on the map. It doesn't matter. So basically, if you choose Redbud, please be aware, make one of these E1 and the other one E2. Okay? So do not make this mistake for Redbud, because Redbud is actually a different elevation for the left half of the building than it is on the right half of the building. Okay? So, all in all, this is how you calculate the vector that I'm looking for, given the coordinate location of a base point and a tilt point and an origin point that I gave you. That's it. Those are the only three pieces of information that we need. The rest we calculate. The next video, I'm going to go over the theory of triangulation. As far as I'm concerned, again, if you choose a building that is not on the CORS map, you're going to have a hard time. It's still possible, but you're going to have a hard time. I will help people with that in person if they want. If you really want to choose a building that's not on the map, let me know via email or talk to me in person or whatever, and we'll talk about it. We'll show up to one of the meetings, and I'll show you how to do it. But for the next video, I'm just going to go over the idea of triangulation and what are some of the benefits to triangulation and what are some of the drawbacks. But for this video, you've learned how to complete the assignment, I will give this um, file to Anka, and she can post it on Canvas, or um, I can send it into a blast email, and you can have access to this as well. Um, for those who are not choosing buildings that are not on the course map, this is the final video that you have to watch. For those who want to choose a more difficult assignment, um, I'll see you in the next video.